So maybe I think after CRE we will start the material balance immediately. But material balance doesn't take this much time. So since weightage is little less, we can do it in, let's say, maybe less than roughly 10 to 15 classes. So how many subjects are done in Vani? So rest the entire syllabus is completed, or? So how many subjects are completed with these 4 subjects? Okay. So somebody is saying 3. So, okay, good, good. Okay, heat transfer, thermodynamics, chemical technology. Okay, okay, good. Mass transfer is not done. Okay, okay. See, one thing I would tell you is maybe I think maybe a couple of times later I will take you. Let's say what is the weightage for the rest of the subject, and then mass is something which is extremely important for gate point of view. So because if you try to see out of 100 marks, generally 75 marks are is technical and 25 marks is aptitude plus, let's say, mass. Clear? So mass is which is extremely important. So for a good gate rank, suppose if you want to get, let's say, less than 100 rank, how many marks you need is 60 to 65 marks is something which is required. You don't need to score 100 out of 100. No, 60 to 65 marks. Less than 100 rank you should target. That is where you will get a good PSU kind of thing. If you're targeting good PSU, then less than 100. Suppose if you're targeting, let's say, masters, MTech, then depends. IITB and IISc generally top picks of the MTechs. So which will be, let's say, less than 100 rank. So after this one will be, let's say, IIT Chennai and IIT Kanpur. So these are the next picks which will be less than 200 to, let's say, 250, 200 rank. Then followed by, let's say, Delhi and Kharagpur. So which are the next will be, let's say, something like 500 rank. So then followed by, let's say, Guwahati and then Roorkee and then all these new IITs. So maybe let's say 1000 to 1500. So basically, so what I would say is if you want to do a MTech, your decent rank should be below 500. So that doesn't mean that below 1000 also is not possible, let's say. So that is something like that. So ICT Mumbai is something which is dynamic in nature because ICT Mumbai has a local driving force more, meaning that they will reserve the seats for Maharashtra people and they will become like the people who are coming out of Maharashtra will become a non-local candidates. So we cannot say particularly for this rank ICT Mumbai will come, but ICT Mumbai is a very good university for chemical engineering, no doubt. It will compete with IIT Bombay and IIScs. Clear. So it is known for chemical engineering. So 60 to 65 marks, what I would say generally is 20 marks you should get in mass plus aptitude. If you get 20 marks mass plus aptitude, you will 99% will get a rank below 100. 99% because your technical load will be only 45, no? 45. Clear. So that is where I would say mass is extremely important. And for mass, what I recommend is previous questions are more than sufficient. Reason because nowadays you have the sets that from last, let's say 5-6 years, you have the sets. That means generally before this one, what happens is the mass will be common for everybody. That means the number of problems that you are getting is less. From last 5 or 6 years, you have the sets. Then what happens is you have so many papers, at least mechanical 4 papers, ECE 4 papers, computer science 3-4 papers. Like this, you have so many papers. Every paper has a mass same, no? So the mass previous questions are more than sufficient. If you could able to solve all the previous questions mass, then that should be 100 and 200% sufficient which definitely gives you 20 marks in the weightage. More. So the more you push on the mass, the less load on the technical side. So technically 45 getting is, let's say, out of 75 is extremely easy, not a big deal. But only thing is getting here 25, 20 out of 25 is slightly difficult. So that is why I always recommend maths is extremely important subject for any of the people who is writing the GATE exam. Clear? So that maths, clear? ONGC and all, that is what I'm saying. PSUs below 100 rank I always target, because PSUs, the criteria is GATE rank is criteria. If somebody who gets a first rank and everybody is ready to take it now. Then later on NITs will be, let's say, in the range of 2000, or let's say it depends. NIT, say like NIT Varangal and NIT Tirchi, people will prefer more than, let's say, some of the IITs also. Like NIT Tirchi is generally preferred over some of the new IITs. So that is how. So it is dynamic in nature. We can't say what is the ranks. Clear? So what I would say is put time now onwards. Put time now onwards and spend good amount of practice questions, math and everything. So it is not very difficult to get a rank, let's say, below 500. So for 100 rank, yes, definitely you should little more work hard, because the competition is extremely high nowadays because of the PSUs. Clear? So coming to CRE point of view, so do you see any questions that you, let's say, have not understood in CRE? So we have almost coming to the, let's say, end of the syllabus. Maybe I think I may need 3 or 4 sessions from now onwards, because today or tomorrow I will complete the chapter 5. After this, one session will be I need on the non-isothermal reactors, and one session will be enzymatic reactions. Maybe one more session problems. If you want more problems, I can take 1 or 2 sessions more. So that is how the CRE is. If you have any doubts from now onwards, what I said as per yesterday's discussion is start reading from now onwards. Start reading from, let's say, first class onwards. So read the entire CRE. If you have any, connect the dots. Always you should read a subject something like this. What is the objective of this subject? How do I use this subject in my practical nature? So always remember, like, practical application is something which is lets you to remember very easily. So what is the objective of, let's say, my CRE? I have to design a reactor. Then for designing of a reactor, so if you see, I have designed the chapter 1, 2, 3, 4, 5 in such a way that every chapter has a meaningful, let's say, outcome. What is my chapter 1 outcome? I need to find out the kinetics. What is my chapter 2? I am designing a reactor for a simple reaction A gives B. So what is chapter 3? So I am designing a reaction for a complex reactions of multiple series reactions. What is chapter 4? So whatever I have designed the reactors which is of, let's say, not useful in practically, so how do you translate them into reality? That is what is chapter 4. So chapter 5 is catalytic reactions. If you have a catalyst, yes, temperature and pressure effects is what is non-isothermal reactors that we will study. Clear? So just read the yesterday last problem that we have solved. We will solve one more problem in the similar lines. Yesterday we have solved one problem, which is how to find out, let's say, mass transfer is controlling, or let's say diffusion is controlling. Which one is controlling the rate of reactions? So we'll solve another problem in the similar lines. Just I'm giving 1 minute time so that you will read yesterday's problem, because the next problem will be in the similar lines. So write this problem. Write this problem. The first order reaction A gives R. The first order reaction A gives R is run in an experimental mixed flow reactor. Is run in an experimental mixed flow reactor. Clear? Find the role played by the pore diffusion. Find the role played by the pore diffusion in the runs given below. In the run given below. Find the role played by the pore diffusion in the run given below. CA naught is 100 and W is fixed. CA naught is 100 and W is fixed. Agitation rate was found to have no effect. Agitation rate was found to have no effect on the reaction. Agitation rate was found to have no effect on the reaction. So this is the given data, dP, Fa naught and Xa. So what is the pellet diameter? Fa naught and Xa. This is the data given. So you need to find out what is the role of pore diffusion, meaning that let's say strong pore diffusion resistance, or let's say weak pore diffusion resistance. So which one? Say CA naught is 100, it is given. CA naught is 100 and W is fixed. Weight of the catalyst is fixed. Here, what is difference between previous question and here? This question is rate is not given. You need to find out rate. So you need to find out. So I started getting the answers weak pore diffusion, but the answer is strong pore diffusion. So everybody will get this question as weak pore diffusion, but the answer is strong pore diffusion. Very technically, very good question. So what is CSTR equation? W by FA naught equal to XA by minus RA. But how do you write this minus RA is minus RA without diffusion into effectiveness factor. This is what you write now. So now I will find, I don't need to find out I need to find out minus RA. So what is minus RA is FA naught into XA by W. So for the first run, what is given is, what is minus RA1 is FA naught is 2 into XA is 0.8 divided by W, which is constant. So this is 1 by 6 by W. What is minus RA2 is 0.4 into, or let's say 4 into 0.4 divided by W, which is 1.6 divided by W. Clear? So what you can say here is diameter dP is changing and my rate is constant. So you tend to answer this question as weak pore diffusion. You tend to answer this question as weak pore diffusion because this implies, this gives like suggestion that let's say it is weak pore diffusion. No, is everybody done till now? Now Now just let's take a step back and see once. Are you keeping rest of all the values constant? Are you keeping rest of all values constant? Is a question that you should ask. So temperature, you are maintaining it as constant. RPM has no effect. RPM has no effect. Then what are the factors which affect rate of reaction? Then concentration. Is your concentration constant for the both the runs? Are you keeping the same concentration constant? Is your concentration constant for both the runs or varying? Varying or constant? See, CA naught is constant. Doesn't mean that the concentration is constant. No. But what is for CSTR, what is important is the outlet concentration. So for the first run, what is CA out for the first run is CA naught into 1 minus XA, which is 100 into 1 minus 0.8. So which is 20. So what is CA out for the second run is CA naught into 1 minus XA, which is 100 into 1 minus 0.4, which is 60. So your CA naught is concentration is varying. So basically your CA is varying in both the runs. First run it is 20, second run it is 60. Yeah, by comparing Thiele modulus also you can solve this question. So the question is this one. Now this is, what is the given matrix is, your concentration is increases by 3 times. Your diameter is increases by 3 times. Clear? What is the effect on the, what is the rate that you are observing is constant. So your concentration is increases by 3 times. Rate diameter is changes by 3 times, but you are observing your rate is constant. Now concentration increases by 3 times. Or let's take diameter changes by 3 times. What will be the effect on the rate? You will have two options. One option is, so your rate is constant. Or let's say one option is no effect on rate. What is second option? Your rate decreases by 3 times. These are the two options that you have. Suppose if you are under weak pore diffusion region, your rate is constant. If you are under strong pore diffusion resistance, your rate is decreases by 3 times. Decreases by 3 times. Two options. Like this, what are the options when you change the concentration? How do you write rate? rate is equal to K double prime into CA into effectiveness factor. So effectiveness factor has two options, either 1 or let's say 1 by M into dP. Do you have any option for concentration? No option. So the only one option you have, that is rate should increase by 3 times. Now let's check here. You have two options, 1 and 2. So if you take 1 and 1, then concentration changes rate by 3 times, diameter doesn't change the rate, then what you should observe outlet is rate should increase by 3 times. So are you observing rate increases by 3 times? No. So either 1-1 combination, 1 plus 1 combination should change overall rate by 3 times. Whereas 1 plus 2 combination. So I'm talking about this 1 plus 1, I'm talking about this 1 plus 2. This 1 plus 2 should give rate as constant, which is what in reality, no? This is what you are observing in reality, because your rate doesn't change. So my rate is not changing. Doesn't mean that diameter is not affecting the rate. Basically what happens is diameter increases by 3 times. So which is decreasing your rate by 3 times. But why you are not observing in your experiments? Because your concentration simultaneously increasing the rate by 3 times. So the answer is strong pole diffusion region, because your diameter is affecting the rate. But why you are not observing? Because there is another effect which is coming into picture, that is the concentration. Spend some time here. So I'm going to give, let's say, 2-3 minutes here. Digest the answer. I will explain again. Slowly understand, spend time. These type of questions you have to spend time, slowly think over this one and understand. Clear? So I'll explain one more time, but yes, diameter and concentration both are affecting. I'll explain one more time all the problems. Spend time and understand. So I'm giving, these are the questions, some of, let's say, technically very good questions, because this kind of questions will give strong explanation of the technicals. So I'll explain one more time. So this is the given data. Diameter is 2 and FA not XA. So rate we need to calculate basically. So I have calculated the rate here. So how do you write rate? Rate of the reaction is FA not into XA by W. So which is 2 into 0.8 divided by W. So which is 1.6 by W. So like this, I am observing rate same. Then you will get a misconception here. I am changing the diameter, but my rate is constant. So you tend to answer this question as weak pore diffusion. Then I asked one question, are you keeping rest of the parameters constant? Is everything constant? Suppose if you keep every value constant and you are only changing the diameter, then if your rate doesn't change, that means it is weak pore diffusion. So what are the parameters which affect? One is temperature, another is RPM, another one is concentration. Temperature is constant. RPM has no effect, it is given in the question. So what is concentration is CA naught is constant. Concentration, if you see, CA naught is constant. But what matters me in CSTR is the outlet concentration, not let's say the inlet concentration. So what is outlet concentration in the first one is 20 because CA naught into 1 minus XA, another one is 60. So then what comes to next point is, so I'm changing my concentration by 3 times. This should affect my rate by 3 times. Clear? So this is, there is no question because minus R equal to K double prime into CA into epsilon. So this epsilon has options. If it is weak pore diffusion, epsilon is 1. If it is strong pore diffusion, epsilon is 1 by m into dp. But concentration has no option. So concentration changes by 3 times. Diameter changes by 3 times has 2 options. Either it can change the rate by 3 times, or it decreases the rate by 3 times, or it has no effect on the rate. Now, if assume that let's say weak pore diffusion, then what happens? You should observe your rate increases by 3 times, no? Because diameter should not have no effect on the rate. Concentration should increase the rate by 3 times. So 3 times no effect. What is the effect is rate should increase by 3 times. This is not you are observing. Suppose assume that strong pore diffusion, then what happens? Concentration should change the rate by 3 times. Diameter should decrease the rate by 3 times. So rate should be constant. That is what you are observing. So you observe, let's say your observation of strong pore diffusion is in line with your observation. So my diameter is decreasing the rate by 3 times, but I am not observing in my overall rate because my concentration simultaneously increases the rate by 3 times. So basically my concentration changes the rate by 3 times. Rate decreases by 3 times by diameter. That is why we are not observing any change in the rate. You can solve these problems differently also. Let's say, assume that let's say you are under strong pore diffusion region. Assume. Then what is your equation? W by FA naught is equal to XA by K double prime CA into 1 by M into dP. Clear? So what is W? W by FA naught is first point. First experiment is FA naught is, what is first point FA naught? 2, no? This is 2. What is XA is 0.8 divided by K double prime is into what is CA is 20, no? Into 1 by what is M into dP is 2. So what do you get? Let's say M W by 2 is equal to 0.8, 2, and first one is what? 10, no? So 10, then 0.8 into m divided by 10 into k double prime. So if you put all the constants on one side, w k double prime divided by m is equal to 1.6 divided by 10, which is 0.16. This is the value. Now from the second experiment, w by what is, this is Fa naught is 4, this is concentration is 0.4, k double prime into what is, second one is 60, what is the diameter is m into dp is 6, 6 and 10. So what you will get here is w into k prime divided by m is equal to 1.6 by 10 again, 0.16. So you are getting same values, no? This says your assumption is correct. If you do the same analysis for a weak for diffusion, you will not get the same values. In weak for diffusion, what happens? You do not have this 1 by mdp is 1. So then w into k prime values from first experiment, second experiment, get both will be not matching. That says your assumption is wrong. So everybody understood this question? We'll solve another problem. Write this problem. A packed bed reactor converts A to R, a packed bed reactor converts A to R by A to R by first order reaction in strong pore diffusion regime to 63.2% level. To 63.2% level. A packed bed reactor converts a first. So I will read the question again. A packed bed reactor converts A to R by first order reaction with 9 mm pellets in strong pore diffusion regime to 63.2% level. If 18 mm pellets are used, if 18 mm pellets are used, what is the conversion? See here also in this question, if you see strong pore diffusion regime is given, doesn't mean that strong pore diffusion means you should not consider it as diffusion strong. Resistance is strong. That is why yesterday also I am saying that confusion is still there. So strong pore diffusion means strong pore diffusion resistance. Resistance is strong. If somebody has not attended the yesterday's class and if you are trying to attend now, then it is slightly difficult to understand these problems. Packed bed reactor means what? PFR or CSTR? PFR. You don't need to convert meters, millimeters and all because these are, I think you should use two equations, use one by equation, another one. All the unknowns will cancel. So answer is 39.3. So how do you write the equation is W by FA naught is equal to 0 to XA dXA by K into CA naught into 1 minus XA into 1 by M into dP. So what are the constants if you bring on one sides? M. All these are, let's say, constant for both the runs. FA naught and everything. FA naught, this one. So W into K divided by M into FA naught is equal to CA naught and all. CA naught. So what do you get here is minus dP into ln of 1 minus XA. Clear? So basically, so what you can write it as dP into ln of 1 minus XA is constant. So first one, 9 into ln of 1 minus 0.632, which is equal to 18 into 1 minus XA. What is XA? Everybody solve this problem? This is only one board, no? So answer is 39.3. So basically, here conversion decreases, no? Because if diameter increases, then what happens to your phi? Phi decreases. Then what happens to your rate? What is your rate? K into Ca into 1 by phi. No, your rate will also decreases. If your rate decreases, then your conversion should also decrease. So if your diameter increases, then your XA decreases. So if somebody is getting 86, then it cannot be right. So next one. So what we have done, this entire derivations are for a first order reaction. So what we have done, all these entire derivations are for first order. So what we got as effectiveness factor is 1 by 5. Then what we have written is minus R equal to KCA into 1 by 5. So what will be happen if you have a general nth order reaction? We are not going to derive that equation. So I am going to write this equation directly from the textbook. So minus RA equal to KCA power n into epsilon for an nth order. After substituting epsilon for nth order, what you get is 2 by n plus 1. So no need to remember this equation. So I am saying no need to remember this equations. K double prime divided by L square whole power 1 by 2 CAS power n plus 1 by 2. N plus 1 by 2. So an nth order reaction, these equations are for strong pore diffusion region or strong pore diffusion resistance. So this epsilon n is derived and substituted here. No need to remember this equation. But what is your observation? Is nth order reaction behaves like n plus 1 by 2 in strong pore diffusion region. This is your observation. An nth order reaction behaves like n plus 1 by 2 in strong pore diffusion region. So for example, a zero order reaction, if you take zero order reaction behaves like half order. First order reaction behaves like first order only. No change. That is what you observe, no? KCAS into 1 by 5. KCAS into what is 1 by 5 m into dP. So after substituting epsilon, there is no change in the concentration power. So that is the for the first order reaction. Suppose if you take second order, will behave like third order. All these changes are in strong pore diffusion region. So if you take a normal zero order reaction, it behaves like half order. If you take a first order, it behaves like first order. If you take second order, it behaves like a 3 by 2 order in strong pore diffusion region. Another change, I think somebody is asking to show the screen. So an nth order reaction behaves like n plus 1 by 2. This could be a 1 mark important question, not given till now, but a good question to be expected in GATE. So another point is, another change in, let's say, strong pore diffusion region is, yes, third order behave like a second order, correct. Strong pore diffusion, the activation energy that you observe will be half of the activation energy that you observe. The activation energy that you observe is half of the true activation energy. The activation energy that you observe is half of the true activation energy. So with this one, first part of the, let's say, fifth chapter is done. What is next part is surface mechanisms. Surface mechanism. Surface mechanisms. So this is the second part. Suppose if you take a reaction, let's say A plus B gives, let's say, C. So what are the resistances that are coming into picture? Let's say three resistances. One is film resistance, another one is diffusion resistance, another one is reaction resistance. Let's say film is not controlling and diffusion is also not controlling. Then reaction is controlling the rate of reaction. Let's say film is not controlling, diffusion is not controlling, then what is controlling is the reaction. How do you know that film is not controlling? Because I have changed the steering speed, then I observed there is no change in the rate. I have changed the diameter, there is no change in the rate. Then what is controlling is the, what is controlling the rate of reaction is the reaction. Clear? Now within the reaction, how reactions takes place on the surface. How reactions takes place on the surface is, there are three steps. One is adsorption. Another one is surface reaction. Third step is desorption. So there are three steps. First step is adsorption of reactants, surface reaction. Next thing is desorption of, let's say, products. So these are the three steps. Desorption of products. So these are the three steps: adsorption of reactants, surface reaction, desorption of products. Clear? So this is how, let's say, how reactions takes place on the surface. Then, so right up to this point, then there are two mechanisms. There are two mechanisms There are two popular, two, I don't know, this pen is, two mechanisms. Two mechanisms are there which popularly explains how reactions occur on the surface. One is Langmuir-Hinshelwood mechanism. Another one is Ehlers-Danlos mechanism. What is difference between these two is, suppose if I take a simple reaction of, let's say, A plus B gives C, A should first absorb on the surface, which is A dot S. B also absorbs on the surface. S stands for site, which is B dot S. Then A dot S plus B dot S reacts, forms C dot S plus S. Then C dot S dissolves from the surface, which is S. So if you see this surface, catalytic surface, something like this, let's say this is a metal sites. These red dots are this is a surface where metal sites are, let's say, metal sites. Then what this mechanism says is, A should sit here, B should sit here. These will react, forms, let's say, C. So what is Langmuir-Hinshelwood mechanism says is, everything happens on surface. There is no gas phase interaction. Then what is Ehlers-Danlos mechanism says on the contrary to this one is, so but nobody knows what happens on the surface is reality, nobody knows. What Ehlers-Danlos mechanism says is, A can sit on the surface, B will still can be in the gas phase, forms C, which is on the surface. So that means this is a surface and gas phase interaction. No, there are multiple possibilities. No, why A should sit on the surface? Then B can sit on the surface, A can be in the gas phase, forms C, which is also on the surface. Then what is another possibility? A can sit on the surface, B in the gas phase, form C, which is still on the gas phase. What is another possibility? So B sits on the surface, A is in the gas phase, form C, which is on the surface. So basically what it says is, it is interaction between surface and gas. What Ehlers-Danlos mechanism says is, it is an interaction between surface and gas. So these are the two popular mechanisms which explains how reactions occur on the surface. So basically what we started with is surface mechanisms. When do you study surface mechanisms? Let's say film is not controlling, then diffusion is not controlling, then reaction is controlling. What are the parts, how reactions occur? Reaction itself is a multiple parts: adsorption of reactants, surface reaction, followed by desorption of products. Then there are a lot of mechanisms available. Basically, there are two mechanisms which explains how surface reaction occurs on the, or let's say how reactions occurs on the surface. One is Langmuir-Hinshelwood mechanism. Another one is Ehlers-Danlos mechanism. What is basic difference between these two is, Langmuir-Hinshelwood mechanism says, first all the reactants should adsorb on the surface, then only reaction occurs. What Ehlers-Danlos mechanism says is, if I have two reactants, there is no need of, let's say, all the reactants to occur on the, let's say, on the surface. A can sit on the surface, B can still be in the gas phase and form C. So here multiple possibilities are there, but in the Langmuir-Hinshelwood mechanism, there is no multiple possibilities. There is only one possibility, because A, B and everything happens on the surface is the fundamental rule. Here it is an interaction between surface and gas. Surface and gas is the basic concept. Then what is next step? Let's assume one of the mechanism and derive the kinetics. That is what is called a surface reaction kinetics. Remember, this surface reaction kinetics is applicable only if film and diffusion are not controlling. Suppose if film and diffusion controls, there is no need to derive the kinetics, no? Because there is no point in deriving the kinetics because film or diffusion, any one of them is controlling, no? So what is next step is derivation of the kinetics. That is kinetics derivation. So let's assume one of the mechanism, let's say is assume that LH mechanism, but this the kinetics derivation will be same even if you do, let's say for LE radial also. Let's assume that LH mechanism, then what is the mechanism? A plus S gives A dot S, A dot S plus, or let's say B should also absorb on the surface, B plus S gives B dot S, A dot S plus B dot S gives C dot S plus S. S stands for site. S stands for, let's say, site. So what is C dot S gives is C plus S. So this is the mechanism. Now we need to derive the kinetics. For kinetics derivation, we need to consider one of the rate limiting step. Let's assume that this is what is rate limiting. One of them will be rate limiting, no? Because these three should occur in series. Adsorption followed by reaction followed by desorption. All these three occur in series. So let's assume that this is rate limiting. What is meant by rate limiting? What is meant by rate limiting? This is the slowest step. This is the slowest step. Then rest of the steps will be fast enough. Rest of the steps will be fast enough. They will reach equilibrium. So rest of them all are reaching equilibrium because they are fast. This is also fast. So the one which is rate limiting is always the slowest step, which governs the overall rate of reaction. Then let's take let's take this reaction. Let's write the equilibrium. How do you write equilibrium? Let's say forward rate constant is Ka, backward rate constant is K minus A. What is Ka is adsorption constant. What is K minus A is desorption constant. So what is Ka is adsorption constant. What is K minus A is Desorption constant. Clear? Then how do I write the equilibrium equation is Ka into Pa, because this is a gas phase reaction. So instead of concentration, I am writing partial pressures. Cs. Cs Pa Ka is equal to K minus A into CAS. What is CA stands for is concentration of vacant sites. What is CAS is concentration of sites occupied by A. What is CAS is concentration of sites occupied by A. What is CS is concentration of, what is site? What is site stands for is, if you take the catalyst surface something like this, you have the metals. Metal is dispersed, no? Each one is a site. This is what you call it as sites. So how does surface looks like? Some of them are occupied by B, some of them are occupied by B, some of them are occupied by C, some are, let's say, vacant. So what CS stands for is concentration of vacant sites. What CAS stands for is concentration of sites occupied by A. So we are deriving the kinetics. So next part is, now how do you write this equation is Ka Pa Cs is equal to K minus A CAS. So what I'm trying to explain here is, so I'm trying to, because these two are reaching equilibrium, for the equilibrium what is forward rate is Ka Pa Cs, what is backward rate is K minus A into Cas. So what is K forward rate by backward rate? What it will become? Ka by K minus A Pa Cs is equal to Cas. What is forward rate by backward rate will become, let's say, capital Ka, which is called as adsorption equilibrium constant for A. Adsorption equilibrium constant for A. Then what is this Ka Pa Cs, which is equal to Ca dot S. This is one equation. Similarly, can you write for B? Can you write for B? So what it comes for B, I am not going to write the full because the derivation is same. Kb Pb Cs is equal to Cb dot S. Correct or not? S is suffix of C, concentration of sites. CAS, CPS. But that is forward rate is equal to backward rate. No, how did you write this one is forward rate is equal to backward rate. I'm not writing anything, let's say, different. Now for C we will write. What is C equation? C dot S. What is PA is partial pressure of A. Instead of concentration, I am writing partial pressures. What is C plus S? So what is concentration of S is C plus S. Now, what is forward? Here forward will be K minus C, backward will be KC. Because forward is desorption coefficient, backward is absorption coefficient, because forward is desorption. So I am following the same notations. So what is K minus C? CC dot S is equal to KC plus PC into CS. What is KC is adsorption coefficient of C. What is K minus C? Desorption coefficient of C. So what this is desorption coefficient, this is adsorption coefficient. Now I will send this to this side. So then what happens? C dot S, this is capital C, PC, CS. So what is capital C is adsorption equilibrium constant. So if you try to observe here, even though C is writing, C is dissolving, I am writing adsorption equilibrium constant because I can use the same K value. I can use the same K value. C is actually dissolving, but I am writing it as adsorption equilibrium constant. So C is dissolving, but I am writing it as equilibrium adsorption equilibrium constant because for A and B and C, I can use the same K value. P stands for partial pressure. PC stands for partial pressure of C. Now, what is my rate of overall reaction? What is my rate of overall reaction is overall is governed by this reaction. A plus B gives C, C dot S plus S. Let's assume some rate constant K. So K into C A dot S, C B dot S. That is my overall rate expression. This is what is kinetics that we want to derive. What is CAS? How do you write CAS? K into CAS can be written as KA, PA, CS, KB, PB, CS. Can you measure PA? I can measure partial pressure. Can you measure PB? I can measure partial PB. Can you measure concentration of sites? You cannot measure the concentration of sites. So if I rearrange this one, K into KA, KB, PA, PB, CS square. Can you measure the concentration? So you cannot measure concentration of vacant sites. You cannot measure concentration of vacant sites during the reaction. Clear? So that is how do you write this values. Now let's write a site balance. Let's write the site balance. What is site balance is CT, which is total number of sides. You can measure this one because you know how many metal sides you have added. So the total number of sides CT is nothing but some of the sides are occupied by A, some of the sides are occupied by B, some of the sides are occupied by C, some of the sides are vacant. This is what is your side balance, no? Total number of sites is equal to some of the sites are occupied by A, some of the sites are occupied by B, some of the sites are occupied by C, some of the sites are vacant. Now let's write CAS. What you can write CAS is KA, PA, CS, KB, PB, CS, KC, PC, CS plus CS. Right up to this point. So if you take CS common from all these equations, take CS from common from all these equations, then what you get CS as CT divided by 1 plus KAPA plus KBPB plus KCPC. So what you get? So what you get CS is CT divided by 1 plus KAPA plus KBPB plus KCPC. Clear? Now take the CS and substitute in my rate overall equation. What it happens? K equal to KA, KB, PA, PB is equal to CT square divided by 1 plus KA, PA plus KB, PB plus KC, PC whole square. Now all these are constants. I'll combine all this into a single constant of capital K, K into PA, PB divided by PB divided by 1 plus KAPA plus KBPB KCPC whole square. Rate overall. This is what is called as kinetics. Kinetics if surface reaction is controlling. If surface reaction is controlling. Suppose if let's say adsorption is controlling, if adsorption is controlling, then it is a different story. Did everybody get? Derivation is very simple. Only thing is it is a lengthy derivation. CT stands for total sides. CT square. Yeah, CT square and all. This is not there. So this and all will be combined. These are constants, no? These two I have combined into a capital constant, which is capital K. Now, looking at this equation also, I can say whatever the terms which are in the denominator, this denominator terms, this denominator says A, B, C on the surface. Now, if you carefully observe the derivation, Where the denominator is coming? Denominator is coming from the side balance, no? Suppose if you observe here in the derivation, here there is no denominator. In my rate expression, there is no denominator. Now, where the denominator is coming? When you write the side balance, no? When you substitute side balance. So this denominator gives clue what are all on the surface. So you can say what are all on the surface. A, B, C are on the surface. I think we will stop it here, and maybe I think there is little further continuous to this one. At time t equal to 0, what is the rate? So that and all we will do it tomorrow. So I'm showing, let's say, derivation again from starting point. This is kinetics derivation for LH mechanism. Now within the LH mechanism, there are multiple possibilities. If adsorption is controlling, another mechanism. Desorption is controlling, another rate expression. Let's say I've taken rate surface reaction as lowest. Then I have derived, let's say, adsorption balance, then A balance here, then C balance here, then overall rate here, overall rate, then adding the side balance. Maybe I'll take 1 or 2 minutes more. I will complete that rest of the part also. Now, what is my rate at time t equal to 0? Then what happens is capital K into, this is PA naught, this is PB naught divided by 1 plus KA PA naught plus KB PB naught plus KC PC naught. But PC naught is 0, no? There is no PC naught at time t equal to 0. Then what happens is K into PA naught PB naught divided by 1 plus KA PA naught plus KB PB naught minus R at time t equal to 0. Suppose if feed is A by B in the molar ratio of 1:1 mole. If feed is A by B 1 mole is to 1 mole, then what happens? What happens to your PA naught? PA naught is nothing but mole fraction of A into PT. What is PT is? Let's say total pressure. What is mole fraction of A? Half into PT. What is PB naught? Half into PT. Then what is my R at time t equal to 0 is capital K into half into PT, half into PT divided by 1 plus KA half into PT, KB half into PT. Now, what happens here is, these are all constants, no? This is a constant. So all these are constants. If I combine all these constants, then what happens is, what happens is, minus R at time t equal to 0 is A into simple PT squared divided by 1 plus B into PT whole square. This is, can be, what is this is? Rate at time t equal to 0 as a function of, this is whole square. Here you have whole square. Whole square is there. Clear? This is rate at time t equal to 0. I think we'll stop here. We will continue tomorrow. So basically what I'm doing is, from this derivation, let's say, overall rate expression, I put, let's say, at time t equal to 0, this is PA naught, this is PB naught. PC naught is 0, but PA naught can be written as mole fraction of A into total pressure. Let's assume that mole fraction of A is half. Even if it is not half, basically they are constants. Clear? Then if you substitute this, then you will get the APT square into BPT. So we'll close here and we are open for, let's say, doubts. What I can do is, I think we will stop it here. You read this derivation once. I will take your doubts tomorrow, because once you read the mechanism, then only you will get more of the doubts. Clear? This derivation is important for gate, but remember, this is first time only will derive like this. Tomorrow onwards, I will show you some shortcuts so that you don't need to derive, let's say, this much amount of, let's say, derivation. So I am showing all the boards once. Fourth reaction is desorption. Okay. So I am not taking doubts now, because you have to read this mechanism, derive this mechanism, then only we'll get the doubts. So I'm closing the session here, please. So we'll take the doubts tomorrow. Once you read the entire mechanism, I will take your doubts. Clear? So I'm closing here.